In this video, we're going to talk about the basics of NMR spectroscopy. NMR spectroscopy is useful for identifying the carbon-hydrogen framework of an organic compound. Now, it only works with certain nuclei, and that is nuclei either with an odd number of protons or an odd number of neutrons. So let me give you some examples. So nuclei such as hydrogen, carbon-13, nitrogen-15, fluorine-19, and phosphorus-31. These nuclei either have an odd number of protons or an odd number of neutrons, because as you can see, the mass number are all odd. And the mass number is the sum of the protons and the neutrons. So let's take a look at carbon-13. So carbon-13 can work with NMR spectroscopy, but carbon-12 cannot. Every atom of carbon has an atomic number of 6, and as you recall, the atomic number represents the number of protons. So carbon-13 has 6 protons and 7 neutrons. The mass number 13 is the sum of the protons and the neutrons. Carbon-12 has 6 protons and 6 neutrons. Carbon-12 does not have an odd number of protons, nor does it have an odd number of neutrons. So carbon-12 does not have a property called spin. Therefore, its nuclei will not be, you can't use it in NMR spectroscopy. Carbon-13 has an odd number of neutrons, so therefore you can use carbon-13 in NMR spectroscopy. Now before we go into carbon-13 NMR, typically you'll learn proton NMR or HNMR. Now hydrogen has a mass of 1. This is the most common form of hydrogen. There are isotopes of hydrogen like deuterium and tritium, but we're going to talk about this particular hydrogen atom. It has only 1 proton, no neutrons. So you can think of the hydrogen atom, or the hydrogen nuclei rather, as a proton. And a proton has a positive charge. And it has a property called spin. And if you studied physics, you know that a moving charge creates its own magnetic field. So you could think of the protons as generating their own magnetic field. Now let's say if we have a sample of protons. So these protons, their magnetic field will have a random orientation. But what happens if we take these protons and put it in an applied magnetic field? What's going to happen? If we place them in an applied magnetic field, let's say it's going in the upward direction, we'll call it B naught, then the magnetic fields of the protons, they could do one of two things. They can align with the external magnetic field, or they can align against it. Whenever the nuclei are aligned with the applied magnetic field, this is known as the alpha spin state. And whenever they're aligned against the external magnetic field, this is known as the beta spin state. Now, as you can see, the alpha spin state is lower in energy than the beta spin state. And so the majority of the protons or the hydrogen nuclei will be in the alpha spin state because it's more stable. And what helps me to remember this is using the analogy of a river. It's easier to swim in the direction of the current rather than to go against it. So whenever the spin is aligned with the applied magnetic field, it's going to be in a more stable state. It's going to be more it's going to be lower in energy. But it's going to be harder to go against the applied magnetic field. And so it takes more energy to do that. So thus, it's in a higher energy state. Now, delta E represents the difference in the energy of the alpha spin state and the beta spin state. Now, that difference in energy is dependent on the strength of the applied magnetic field. So as you increase the strength of the applied magnetic field, delta E will increase. And so you're going to have greater separation between these two lines. Now, what does it take for a hydrogen nuclei to switch from the alpha spin state to the beta spin state? What you need is energy, particularly radio frequency energy. So if you add RF energy to a proton, and if it's the right amount of energy, it can flip from the alpha state to the beta state. Now, if the nuclei falls back from the beta state to the alpha state, it can emit radio frequency energy. But it takes radio frequency energy to promote it from the alpha state to the beta state. And so when it's constantly flipping back and forth, it's in resonance. Thus we have the term nuclear magnetic resonance. So just remember that as you put energy into the hydrogen nuclei, you can promote it to the beta state. And as it falls back down, it's going to release energy. Now, if we want to, we can calculate the energy difference between the alpha state and the beta state. And here's the formula that we could use to do so. The energy difference is going to be Planck's constant times the frequency of the energy that we're going to use to put into the protons in the alpha state. Now, the frequency that we need is going to be equal to the gyromagnetic ratio divided by 2 pi times the strength of the applied magnetic field. And so you can see that delta E, the energy difference between the two states, is proportional to the applied magnetic field. Now you might be wondering, what is gamma in this particular equation? So this represents the gyromagnetic ratio of the nucleus that you're dealing with. So in the case of the hydrogen nucleus, the gyromagnetic ratio is going to be 2.675 times 10 to the 8 Tesla to the -1 times seconds to the -1. Now, for the carbon-13 nucleus, it's different. It's going to be 6.688 times 10 to the 7. And so it's less than that for hydrogen. So that's the formula you could use if you wish to calculate the energy difference between the alpha and the beta spin states. Now, sometimes you may need to calculate just the frequency that's needed given the strength of the applied magnetic field. And it's going to be the gyromagnetic ratio divided by 2 pi times the applied magnetic field. So you can also use this formula if needed. Now let's work on this problem. What is the operating frequency required of an NMR spectrometer that generates a magnetic field of 11.744 Tesla? So to calculate the operating frequency, we need to use this formula. It looks like a V, but it's really the Greek symbol nu. So nu is equal to the gyromagnetic ratio divided by 2 pi times the applied magnetic field. Now, what is the gyromagnetic ratio in this case? Well, we can find the answer here. We're dealing with a proton NMR spectrometer. So for a hydrogen nucleus, it's going to be 2.675 times 10 to the 8. Now the strength of the applied magnetic field is given to us in Tesla. And so that's 11.744 Tesla. And we need to divide it by 2 pi. When typing this in your calculator, make sure to put that in parentheses. So if you type in 2.675 times 10 to the 8, and then multiply that by 11.744, and then divide that by 2 pi in parentheses, you should get this answer. At least that's what my calculator gave me. Now, we could round this answer and say it's approximately 500 million hertz. Now, looking at our answer choices, we need to convert it to megahertz. If you recall, mega is 10 to the 6. So a frequency of 1 megahertz is 1 times 10 to the 6 hertz. So you want to set this up in such a way that these units will cancel. So 500 million divided by 1 times 10 to the 6, or 1 million, is 500. So the frequency is approximately 500 megahertz. So therefore C is the right answer.